Dassault Systèmes is a company that's broken down into a whole load of different brands and products. I'm guessing that many of you are familiar with SolidWorks and CATIA. I'm hoping that you're also somewhat familiar with the Simulia brand that I represent, which includes things like Abacus, FE-Safe, Tosca and iSight. But then we've also got Delmia Manufacturing and Innovia and many other things as well. I'm hoping also that the 12 industries on the right-hand side of the slide look familiar to you, and that actually whichever company you work for slots into one of those somewhere, or maybe several of them. When I look at the world of the people I go and visit, I often see that they've got a CAD system for designing and making shapes, and they've got some CAM system for doing their manufacturing, and they've often got some CAE tools, maybe FEA or CFD. But often they've bought those 3 different products from 3 different vendors, and they don't actually work terribly well together, and they might be quite separate departments that don't really want to talk together. And that's a bit of a shame. And I think you can get away with it just about with traditional manufacturing, but as soon as you're doing something more advanced, like composite materials or additive manufacturing, you've really got to do it all together. And that's why you need one holistic way of doing it. And to illustrate this, I'm going to go right back to the start of my career. And here's a couple of pictures of things that I worked on. This is an axle end from a Land Rover, from a Range Rover in 1993. And this is the starting one, okay? That was what they started, that's what they had on the vehicle. And it was causing problems, and there were some warranty recalls, and it was costing a lot of money. We then redesigned it using integrated CAD and FEA and doing lots of iterations and doing effectively a manual topological optimization. And this is what we came up with. So 2 different products, but they're doing the same thing. What we did, and this was my first brush with additive manufacturing. Obviously, back in these days, we called it rapid prototyping, and it was basically using stereolithography and then plastic parts. So, of course, they weren't functional parts. They were quite useful for feeling the weight difference. And in this case, the weight difference equates to 0.5 kilogram of steel. And bearing in mind there's one on each end of the axle, we saved 1 kilogram of weight. We made it stiffer, and we made it stronger, and we made it lighter. But at the end of the day, these plastic parts were still kind of illustrating, and they're kind of plastic ornaments, if you will, okay? Because you couldn't actually put these on a car. You actually needed real metal. If we fast forward that to today, just about a month ago, I was visiting one of our Formula One team customers, and I was meeting with the additive manufacturing manager there. And he was just supremely frustrated that the designers come to him with products and ask him to make them, but they haven't actually thought about it. They haven't released their mind and been open. They've actually still constrained by old-fashioned manufacturing methods. So he's still trying to teach them to take advantage of the freedom that additive manufacturing brings them. There's a press release that came out in June 2016 that Airbus allowed us to put out about how they had gone through an exhaustive 2-year benchmarking process that culminated with them selecting Dassault Systèmes as their additive manufacturing software provider, okay? Why is that? I'm going to go through some of the details of behind that decision, okay? So this is kind of our view of the world and what we think you need to do this kind of task. If we look out there at the moment, you look at the design side of things, and you look at what's happening in the field, okay? These 2 worlds come together. How do people do this at the moment? They've got all sorts of different files and tools and systems. There's quite a lot of files floating around. Currently, that can often take weeks, if not months, to do it properly. But our customers are saying to us, we don't want that. We want it to take much shorter. We want days or weeks rather than weeks or months. But what do? Is they go to the guys at the additive manufacturing machine, and they scream at them, and they push them, and they put on lots of pressure. But actually, all they're doing is lots of trial and error, and it's quite hard for them to actually do anything transformative. So we actually need to do different tools and take a different approach. And this is why we're doing what we've done. So we thought long and hard about our strategy. What are the ingredients and the component technologies we need? At a very high level, we need to think about ways we can optimize things. We also need to think about what do we get versus what do we want. Sadly, there's a difference. There's a difference there, and we don't always get what we want. We also need to think closely about what actually happens in the machine that's producing these parts, and how do we actually understand that and model it and simulate it. Most importantly, at a very deep level, we really need to understand what's happening to the materials that we're transforming. And we need to have very sophisticated material models, because you're going from something like powdered titanium that you're melting and then you're letting it re-solidify again. So it's going through crazy phase transformations, including crystalline phase transformations. You also need to have very advanced, powerful solvers, ideally both an implicit and an explicit solver, and they need to be able to handle all of those nonlinearities. So in the past, in the recent past, people have been trying to do this using semi-static or semi-collaborative processes, different tools that are kind of stuck together. But there are interfaces, and then there's translations, and then there are losses in translations. So what we want is we need a proper, holistic, integrated system where all of that capability is on one platform. We want to do it model-based. We want to model and simulate as much of it as possible. We want to manage all of the data and the processes as part of that. We want to compare the virtual world and the real world, and everything's got to be connected together. And here's a bit more detail. We need to think about the multi-physics and the multi-scale aspects. I like this phrase about we want engineers to be engineers. And I'm always wary about use of the word innovation, because no piece of software can make anybody innovative, but it can help people who are innovative. It can help them to evaluate their ideas and prove that their ideas are good, or else drop the ideas that are not so good. So to start off with, we're thinking about sort of the design side of things, and a lot of people are talking about generative design already. So we've got this capability in here. We're looking at the design space you can work in, the loads, the conditions, the constraints. We're looking at different ways of exploring what we can get out and what are the different manufacturing methods. We're not always going to go to additive. We might go to casting or milling or something like that instead. So there are different solutions that come out. When we look at the topological optimization, there are simple topological optimizers out there, but we don't believe they're good enough because there are small nonlinearities, and if you include those, they can have quite a dramatic effect on the outcome of your optimization. So you need to include them, otherwise you're missing the mark. We also need to think about, once we've got that topological optimum, how do we actually smooth it down? If you talk to Aldine, this is one of his big bugbears, is these riffly surfaces. So you need to, first be able to smooth them. Second of all, maybe do some quick, direct modeling on it. But ultimately, our customers are telling us what they really want is a proper, feature-based parametric CAD model, okay? And we can get them there. So how do we do this? So this is a process that we call ReCAD. You're basically taking this kind of dumb lockdown model. It's a bit like an imported IGES file, and you're now actually rebuilding it as a proper parametric feature-based CAD model. And if I jump to this part of the animation, you can see we slice through the model, and it builds and it lofts the various different sections, and then automatically rebuilds this model for us. So it's manually controlled, but it's highly automated. So it takes something that could take you hours or days, and it allows you to do it in minutes, but you're still controlling it. We're also thinking a lot about the manufacturing, because this is a whole big design for manufacture exercise, okay? We're thinking about the orientations of the part, the slicing, the laser paths, all of this kind of stuff. And we're making sure that we're thinking about what we're doing and including that as part of our modeling. Okay, we're thinking about how we're positioning parts. Are we having multiple parts in one print run? And are we thinking about the support strategies? I can't compete with what in Topology are doing. They're doing some great stuff there, but we've got some automated support strategies that we can put in there where you can take a template and say, populate that and just extend it and automate that design. So you've got to sort of follow a company standard. Most importantly, we're also looking at what is the actual specific machine doing. In this case, it's a Renishaw machine, but it could be from any other company. And we're making sure that we're modeling what goes on in that specific machine. And all the machines are different. So we have to have different settings that we pull out of libraries. Then we get into the bit that I'm most passionate about, which is the actual simulation of the manufacturing process itself. So you can actually see we're actually adding material, we're doing all of the thermal things as well, and it's some really powerful, complicated simulation that we're running here. So we're looking at all of the thermal effects, because of course you're going through massive thermal fluctuations going on. You end up with all these weird residual stresses that go on between the different layers. you end up with warping and distortion. And you can also end up with problems whereby, because of the way the part moves in the printer, the printer can actually stop. And we want to be able to predict where those errors might occur. We have some customers who are actually having parts that are breaking and failing while they're being printed. And we want to be able to predict if that happens. Because if it's cracking as you're making it, it's not any good, is it? We want to think about what happens to that part once you've made it. You take it out of the machine, you're now going to put it onto an assembly or onto a product, and it's going to have its own in situ stresses applied to it. I mean, you're making it out of metal because you want it to be strong, so it's got to carry quite considerable load. But you've also got to think about those residual stresses that are in it before you've even put your real load on it. And we want to think about the durability and the fatigue and how long it's going to last. And we're also going to think about things like machining away the various different support structures, and also things like post-machining of the parts, such as where you might have a bearing or something, because often the part that you 3D print is not the final part. You've got to do some additional work on it. And you've got to include all of those in your calculation. This is a bit I think is particularly cool, is we see parts that come out of the machine that are warped and distorted. It's an inevitable fact of the way these things are printed. What we want to do is, first of all, we want to minimize that and understand it. But second of all, if we understand it and can predict it, what we can do is we can do a reverse morph. So we actually apply that warping to the part before we print it. And then as it's manufactured, it warps into the right shape as opposed to warping out of that shape. So you end up with the correct shape that you wanted rather than something a bit off. If you think about it now, what we're trying to do is we're trying to simulate the process, we're trying to simulate the physics, and we're trying to simulate all the different materials. I've spoken a certain about metals, but of course there's a wide range of polymers as well. And we worked with a lot of different companies to validate this and do this. Specifically, I'm going to pull out here TWI, who are based here in the UK, and Oak Ridge National Labs over in the USA. But you can see HP, Stratasys, Purdue, ARL, that's Army Research Labs in USA, and Simtech there, like the Singapore equivalent of MIT. So here's a couple of examples, one from TWI and one from Oak Ridge National Labs. These are real products, tested, validated, proven. Okay? It's not us saying it's accurate, it's these people. So you can go and talk to them, and they'll tell you about it. This guy at TWI, Tyler London, he's done a lot of work. You can see here, again, experiments versus simulations, great correlation. On the right here, you can see some defects and some porosity problems that they had that the simulation predicted. So that's perfect. It's spotting the problems before they occur, and then you can do something to try and minimize them or get rid of them. Here's some more work that Tyler London has done. First of all, on wire arc additive manufacturing, and second of all, on laser metal deposition. So he's doing all sorts of different materials, processes, methods, and machines. Oak Ridge National Lab, their glory example was when they decided to create an Seacobra. Got plenty of publicity like this. They basically made pretty much the entire car using additive manufacturing. And this was a factory tour they had. A couple of guests there. If you zoom in, you'll see they had Barack Obama and Joe Biden going to visit them. Obviously, that dates the slide now from a couple of years ago. So we're looking also at all sorts of variabilities and things that we can do. Here you can see we've got one particular part, and we're using 4 different laser paths to figure out different ways that we could make it. What's the best one? What are the different variations? Pros and cons between them all. Let's do that investigation before we start committing time and money to actually making this part. Let's make sure that when we do make it, we make it as best as we can. So if I revisit this whole set of technology components that I spoke about at the start, I think this is a list that I think we need. I think we need generative design. I think we need to be able to manipulate the shape and have a good, powerful CAD system. I think we need a whole host of different simulation tools, such as advanced solving, topological optimization, variation exploration, and durability. And we need a lot of sophisticated, quite powerful manufacturing and production planning and understanding and modeling. Now, as it happens, at Dassault Systèmes, we've got all those. We've got CATIA, SolidWorks, all the Simulia products, and Delmia, all pulled together on the 3D Experience platform. And that then gives us what we think is a very compelling story and a very compelling set of capabilities that seems to be very attractive for many of our customers. If we have a look at sort of our strategy, we're talking not only about additive manufacturing, but about digital manufacturing, end-to-end process, the whole thing, not just little parts of it, but how does it all come together? We're looking at all the various different technology capabilities that we believe are needed to do this properly. And we've developed those, we've acquired them, and we continue to develop them. And then we bring all those capabilities together into a variety of different role-based applications. So we understand who you are and what you want to do, and we put the right tools in your hands. But those are tools that are compatible with the tools that your colleagues are using upstream and downstream from you. So if I give one sort of call to action, I'd say you've all got a copy of this magazine in your little pack today. In fact, I had an issue of it dropped through my door on Saturday. I could recommend you turn to page 32. I'd recommend you read the article written by Lawrence Marks. There's a picture of him, and he's sitting there. He's laughing. And then go to stand number 30 and go and talk to him, okay? He can help you out with a lot of this, okay? And I'm going to leave you there with a warping, producing, animating, photo-rendered example of this part. You can actually see it doing a funny little dance as it goes through its warp. Okay, thank you very much.